Hello and welcome back to Calculus 2 section 6.7 on length of curves. 6.5 length of curves. We can just edit that later. Have you ever wondered, right, what's the length of the road you drive on? The answer is no, because why would you? What is the length of the cord? Well, you know it's either 3 feet or 6 feet, right? For a cell phone charger or so on. So we don't need this, right? Class dismissed. This section is very useful if you want to calculate in nature something that you cannot straighten out. If I have a piece of wire, and I don't want to undo this because we're going to lose the bandwidth and then everything is done and gone. If you want to calculate or measure the length of a piece of wire, naturally you will straighten it, put it against a straight edge, and just figure out its length, and you are done. But let's say it's an art piece and it's not a wire, it's now just some arch made out of glass. You can straighten it, right? But you still want to know the length of it to establish mathematical superiority. So what you can do is you can find what is mathematical function that fits that curve, and then you will integrate in the formula that I'm going to derive, and that formula will give you one-dimensional length of the curve for whatever you're measuring. So now you will know the length of the road, the length of the rope, the length of the wire, or whatever arch that is somewhere made out of concrete or glass or something, and you really can straighten that one. One of the project problems that is on the rotation is to print some function. I even changed that from project to project. You take a piece of wire or a yarn or something, a better wire than yarn, because yarn you can stretch and then so you print some function, could be ln, could be sine, could be polynomial of some kind. You print the function on the paper, and then you bend the wire or a yarn along the printed line. And then you will use calculus to compute the length of the line, which is this section, and because you bent the other line, because you bent the piece of wire on top of the printed line, you can cut it to the top of the function and then straighten it, right? Take it off, straighten it, and measure, and make sure that the calculation you did on the problem and the measurement on the ruler is very close, right, within your measuring error, right? I'm not asking for 6 decimals, but it's one of the cool problems that are very easy to do with minimum issues. So now, how does this work? Well, first we are going to take a look at some random f of x that lives in the xy plane. And you would like to figure out the, let's say, length of curve between A and B. So you are looking for the arc length over here, right? So this is arc, and you are looking for arc length. Now, as it always goes in calculus, you are going to chop this up into infinitely many, infinitely thin pieces, right? And then you are going to observe one of those infinitely small pieces. So what I'm going to do is I'm going to take the little part over here and then blow it up here to see that the curve on top had some change in x and some change in y. And there is, so sorry, this black is actually red. And then there is this line L, and we can use Pythagorean theorem to say that L squared is equal to delta x plus delta y. Delta x and delta y are just the change, right, in x and change in y for this infinitely small cut, infinitely small piece of the wire or something. So from there we see that L is equal to the square root of delta x squared plus delta y squared. So now what I'm going to do is I'm going to add, first I'm going to do a little trick over here. Delta x squared plus delta y squared. I'm going to multiply by delta x over delta x. Out of nowhere. This is like when the magician pulls out the rabbit from the... It would be so good if I had the fairy dust and it's just like, oh. So we multiply by delta x over delta x, and we take the delta x that is on the bottom and we shove it under the square root. It will pick up a square, because when you stuff something under the square root, it picks up the square. If you are kicking it out of the square root, it loses a square, right? So this next step will be delta x squared divided by delta x squared plus delta y squared divided by delta y's, delta x squared, and then you still have times delta x on the outside. This was just algebraic manipulation. And now we are going to add all L's. We're going to add all infinitely many L's, and we do that with the Riemann sum and a summation, and you know that then it becomes an integral, right? So what I'm going to do now to add all L's, I'm just going to say that this becomes summation 1 to n of this square root of delta x squared. Well, delta x squared and delta x squared is just 1 plus, and then I have delta y squared over delta y over delta x, everything squared, and then delta x. And then because I want to add all, let me underline the word all, orange, I'm going to also put the limit, because it is n goes to infinity. Now in Calc 1 you learned that when you have this type of form, it spits out an integral. So length of curve L is given by, and this is your formula to memorize, integral a to b of square root of 1 plus f prime squared, which is the derivative. You clearly see dy dx there is squared. So that's the derivative squared. And then delta x on the outside becomes dx. This is your arc length. And we need the blue one as well. L equals integral c to d square root of 1 plus f prime squared of y dy, just for a good measure, right? The y direction as well. Every formula we learn in chapter 6 has the x integral, y integral, so there they are. So what we did is we approximated the length of a single tiny piece, and then we just added all of them on a pile, which created a Riemann sum, and Riemann sum turns into a definite integral, and we see that what we need to compute is this square root, right? And you also see that whatever function f of x is, right, the one that you are computing the length of, that function is going to, you have to find its derivative, then you have to square it, then you have to stuff it in there, and then, good luck with the rest, right? Because now you have to integrate, and you have to deal with the square root and all of that good stuff. So let's take a look at, 2 examples or so, and then next section is very similar. 80% of the formula looks the same. We're just going to add 2 things in it, and you're done. So, what is a problem that I don't need calculus to solve if I want to know the length of the line? Straight line, thank you, right? So I'm going to pick a straight line, and then we're still going to crank the integral because we can. But then we are also going to calculate using the distance formula. We are going to obtain the same number using distance formula. Now, obviously, that only works for straight line because the distance formula works for the straight line. As soon as you curve, then you can't do the straight line anymore, and then we have to suffer with other no coughing things. So now, let's go with, I can just pick anything, but let's go from 3 to here. 4, 5, 6, 7, 8. So that's 8, 3. I just arbitrarily picked the line segment, and we can immediately calculate the length of this curve using distance formula. I mean, length of the line. And that's going to be the square root of x2 minus x1 squared, so that's 8 squared, plus y2 minus y1 squared. Wait, the other one was 3, so this is 5 squared, right? And this is 3 squared. The change in x is 5, so 5 squared, and then change in y is 3, 3 squared. Good. So square root of 25 plus 9, d equals square root of 24. Right? What happened? Yes, that's what I said. Please pay attention. Thank you. 34. 34 is 2 times 17. We cannot simplify this. All right. Now, why simple if we can just correct the integral, right? So let's. What is my function f of x? Well, we have to find the line, right? Use algebra to find the line because that's your f of x. So to find f of x, we're going to calculate the slope m. Now you know that the slope m is going to be 3 over 5 because the function goes 3 units up, 5 units over. And now you have a point 3, 0. So you can stuff all of this into y equal mx plus b to calculate b, which is the y-intercept. So now I have y to be 0. Then I have 3/5 times 3. And then I have b. So b is negative 9/5. And I have the function f of x, which is y equals 3/5 x minus 9/5. Now I know that for the formula I need its derivative. So I need f prime of x. And that's just 3/5. Yep, joke. So length of curve L is integral 3 to 8 because that's my a and b, right? My length of curve is between 3 and 8. So those are my a and b for limits. 3 and 8, square root of 1 plus derivative squared. Well, that's 3/5 squared, and then I have dx. That's a constant integral, right? Right. So I have 9/25. So this is integral of square root of 34/25. Still 3 to 8 dx. And you can kick integral of square root of 34 divided by 5. See, I computed square root of 25 is 5. And then I have x that goes from 8 to 3. Well, that's square root of 34 divided by 5 times, open parenthesis, 8 minus 3, and that's 5, so square root of 34. So next time someone tells you, what do you know? Just tell them that you can compute the length of the, instead of using the distance formula, you can use the integral. Pull up a chair, right? Do it on a napkin. Let's raise the spice level.
People are already coughing on the spice.
That was integrating a number, so that's hopefully not a cough. Oh, I see you have a support now. If you are using textbook for homework, they clearly marked problems 21 through 32. You have to use technology to integrate. Right? 21 through 32 right? It's all of them have to use technology because you did not learn the integration techniques and stuff. So you are learning to set up. Now, but you do have up to 20, the stuff that you can compute 100% by hand, like I just did. So let's take a look at all right, so this one is not bad. Y equals 1/3 x 3/2 from 0 to 60. We know that we first have to find the derivative because derivative gets squared and stuffed into the integral. So the derivative y prime is, we copy the constant, then put 3/2 x to the 1/2, and this dies, and it is 1/2 x to the, well, square root of x, right? Now you need to square that for the formula. So we'll get there. Length of the curve is integral 0 to 60, square root of 1 plus square root of x over 2, everything squared, dx. Integral 0 to 60, and then you have a square root of 1 plus square root will be killed by a square, so you have x over 4. Dx. Now, how do we integrate this? Okay, and then what? How many integration methods do you know? You know two, basic and U-sub. What is this one? U-sub, right? So U is the mess under the square root. du is 1/4 dx, because derivative of 1 is 0, derivative of x is 1, so just 1/4 dx. I don't have 1/4, so I have to put that 1/4 in and balance it with a 4 on the outside. Now, we are also switching the limits. When you plug in 0, your lower limit becomes 1. When you plug in 60, your upper limit becomes 16. You plug your 0 and 60 for x in your U-sub to change the x variable input into a U variable input, so you don't have to switch back later. So just change the domain completely, including the limits. This becomes square root of U du. So for U to the 1/2, so that's U to the 3/2 divided by 3/2, computed from 1 to 16. This is 8/3, open parenthesis, 16 to the 3/2 minus 1 to the 3/2. 8/3. Square root of 16 is 4. 4 cubed is 64. Minus 1. Well, that's 63 and cancels with 3. So that's 8 times 63 over 3, which is 8 times 21, which is 168.
Why change the limits?
So I don't have to go back to x. Remember how we had the sentence, right? I don't care about U, I care about the x. Every time you integrate, U-substitution, your solution after the U-sub is in terms of U. We don't care about U. We care about x. So you have to switch back to x domain and put plus c. But when you have limits, you don't have to switch back, because you can switch your limits from x to u as well, and then entire integral is in terms of u, and you integrate in terms of u, and you stick u limits inside the u integral, and then you get 168. So if you don't like that, then you integrate u, you go back to x, and then you use 0 and 60, and you still get 168.
You put it into the U function right there. The blue?
Yes, that's why I put 0, 60. When I plug in 0, then I have the lower limit 1. Upper limit was 60 divided by 4, 15 plus 1, 16. So now my entire, as you can see, U1, U2, UU, everything is U. Right? Cool. Yes. If it's a definite integral, and please don't deal in absolute, only sit deals in absolute. If you don't like switching to U domain, the limits, go ahead, integrate U, go back to X, and use X limits. It's more work, obviously, because you have to go back to X. I prefer to switch. If the rest of the problem remains in U, yes. Because we're going to have nested U substitution. You will do a Calc2 thingy-majingy, and then there will be a U substitution followed by another U substitution, call it a G substitution. So you have 3 different integrations back to back, and you started with the limits that went from one domain to another domain to another domain. Yes, so this is why it's really good to switch your limits along the way. We're going to have a trig substitution problem that will present you with a trigonometric integral, and then you will use the U-Substitution, right? So your, I'm just gonna as you kept writing, right? You moving your head, yeah. She kept moving to see me. So for trigonometric substitution later, your problem will start as x. You will switch that into theta, which is sine theta, cosine theta, and so on. And then you will have to use U-Substitution to solve that. So the theta then get moved into U, but your limits were x. So you can't have a U answer and x limits. So the best course of action is you use the U-sub, you change your x's into thetas, then you have to use U-sub to solve that, and then thetas go to U's, and then you just compute in the U and you're done. Otherwise, you have to go, right? You'll see when we get there, right? The short story here, right, is use the substitution equation to change your whatever previous state was into the current state, so you have the most current domain limits. If it's a U, it's U. If it's X, it's X. If it's theta, it's theta. And then you will not have to chase things later and worry, did you change it, did you didn't change it, right? That's one of the things that I, when I see a certain type of an answer on the test, I know immediately that the student didn't change the limits. Okay. Because after this many years, I can spot it like that, right? So our problem was X. We have to use U-sub. We go into U domain with a function, and then we also go into U domain with limits, and it's so damn easy, guys. You're just using the same U-sub, and you just use the bottom number. It spits out the bottom number. You put up the upper limit. It spits out the new upper limit. It should take less than 10 seconds to do that, and you don't have to then unwrap it later, right? Especially when you have nested substitutions, which you will.
So when you have nested substitutions, let's say there was one more substitution after this, then you can find our new U or whatever the variable is, and then substitute 1 and 16.
Yes. Okay. So if there was another G substitution followed by square root of G, you would be computing the bottom as a square root of 1 is 1, and the upper square root of 16 is 4. And then the G limits would be 1 to 4. You can nest as many of these as you want. Linear operator, for some differential equations in green functions, you nest 4 inside. So, yeah. Okay, cool. One more example, and we'll take a break. Let's see, what should we have? Ooh. Lock the doors. Get the sleeves out of the way. Start a new page and have at least 2 colors. Ready? Y equals 2/3 x to the 3/2 minus 1/2 x to the 1/2 on 1 to 9. Share the colors, please. Right? 2 colors minimum on this one. First order of business, as always, take the derivative because that's what you stick inside the formula. So, y prime is, copy the constant, then you drop 3/2 down, x 1/2, minus 1/2, drop the 1/2 down, and then x to the negative 1/2. These completely cancel. Y prime is x to the 1/2 minus 1/4. Well, you can call it root x if you want to. I will let you meditate on the derivative. All right, that's your Calc 1, Chapter 3. Derivatives of, right, n x to the n minus 1. Standard stuff. We copy the first half, we drop the second half, and then x 1/2 minus 1 is negative 1/2. Negative shoves it in the denominator, so that's why the square root for the second term ended up in the denominator. Half times a half is clear a quarter, so not too much discussion there. We are ready to plug this into our equation. We have our limits 1 and 9, right? That's given. And we have a square root of 1 plus, open parenthesis, square root of x minus 1 over 4 square root of x, everything squared, dx. We have to integrate this. U-substitution doesn't work here because there is nothing in front of square root of x to be the derivative of what's under the square root. So hopefully there is another trick, and there is. The only thing we can do here is square the binomial, right? The only thing we can do is to say square root of x minus 1 over 4 square root of x times itself. There are no other options. Square root of x times square root of x is x. Now, minus 2 times the middle term, right? Do we remember a squared minus 2ab plus b squared? Hopefully. So we can skip a couple of steps. So, do you see that when you multiply a and b, they will cancel root x? So you just have a quarter? Do we all see that for the middle term? And then plus the last term is squared, so 1 over 16x. So what do I have? I have integral 1 to 9 square root 1 plus, and in parentheses I have x minus 1/2 plus 1 over 16x dx. Do I need these parentheses? No, I don't, right? So what can I combine? I can combine 1/2, right? And what do I get? 1 minus half is half. You know what? I'm going to keep that half in the middle. So square root of x plus 1/2 plus 1 over 16 over x dx. What now? Here is $1 million trick. I need you to pay attention and then rewind the video 15 times if you need to. Do we all see that these two look absolutely the same, a part of the sign of the middle term? One has positive, one has negative 1/2. Do we all see that? You better, right? Unless, please, anyone? All good? Oh, you got it? Okay. Now, I'm going to write two algebra formulas. One says a minus b squared is a squared minus 2ab plus b squared, and the other one is a plus b squared which is a squared plus 2ab plus b squared. Why did I write this? A plus, yes, nice. Now I really need you to look at this. I'm going to erase this purple and put it pink and put it somewhere else. Look, if the minus 1 came from there, where's the plus 1 gonna go? Into the same one, just with a plus, right? And then you will have a square on everything, and that will kill the root, and you can integrate. Magic. So 109 square root of x plus 1 over 4 root x squared dx. So I'm just gonna give you some time to meditate on this. So if this one gave me that one, and they're the same apart from the middle term, and I know that if the middle term changes, it just changes the sign there, then this has to give me that with a plus, and it does. It's a good time for me to go drink some water. I'll be back. You keep staring until you see it. Question like this is up again in the next section with this kind of trick. And then generally on exam or a final, this is what you know, because we can't do many of these. It's very, you'll see that more than half of your problems for homework, you have to use computer to integrate. So you have the basic line, then you have the x, and you have this, like 3 flavors. This one is a little bit involved, right? Just drink the water. It's literally like not even 10 feet away from the door.
Professor, I have a
Yes,
question.
student.
Would it be? Oh, because he. Yeah.
Yeah. So you can. You don't get to worry because this one, right, and this one, they don't, right?
Well, technically, they get added into the second one, converting it into the.
Yes, but when you are comparing it visually, right?
Yeah. Okay.
It's this negative that gets that negative, and this positive that gets that positive, which are these and these.
Yeah.
That's what's happening. Now you will sit and you will rewind this few times, and it will be better. Now we have just integral 1 to 9, and this is simply going to be x, right? Root kills the square, so square root of x plus 1/4. Well, you know what? X to the half. Let's go. X to the half. X to the negative 1/2. So you can integrate, and we get x to the 3/2 over 3/2 plus 1/4 x to the 1/2 over 1/2. Computed from 1 to 9. So this is 2/3 x to the 3/2 plus square root of x over 2 from 1 to 9. This is 2/3 9 3/27 plus 3/2 minus 2/3 minus 1/2. There we go. That cancels to 9/18. 3/2 minus 1/2, that's plus 1 minus 2/3. 19 minus 2/3. Yeah, 3/2 minus 1/2 is 1. 18 plus 1 is 19. 19 times 3, 20 times 3 is 60, so 57, 55, right? Is it 55 over 3? No, 54. "19 times 3 is 20 times 3, and then you subtract one of the 3's. So that's 57. 57, yeah, 55 over 3. Yes? No? Who cares? Yeah, break. Bye.